Welcome to WikiPodcast. This is the deep dive, and today we're plunging into one of the absolute cornerstones of physics, Isaac Newton's three laws of motion. This is part of our physics series, diving into the foundations of classical physics, exploring the fundamental rules of motion.
And they really are foundational, aren't they? First published in his monumental Principia Mathematica back in 1687, Newton's laws give us the essential framework for understanding why objects move, how they move, and, well, why they sometimes just stay put.
So our goal for this deep dive is pretty clear. We want you to get a solid grasp of each law. We'll look at them in action with some real-world examples, even cosmic ones. We'll also touch on the history, Newton's genius in putting it all together, and, where these laws fit in the bigger physics picture today.
Exactly. And to really talk about motion properly in physics, we need sort of a shared language. Let's just quickly cover the basics these laws build on.
Good idea. It's more than just saying something's moving, right? Classical mechanics needs precision.
Precisely. So we describe motion using position, velocity, and acceleration. Velocity, well, that's how fast your position is changing over time, speed and direction. And acceleration is how fast your velocity is changing. So speeding up, slowing down, or even just changing direction. That's all acceleration.
Okay.
And crucially, these are vectors. Direction is just as important as the number itself.
And the thing that causes acceleration, that's force, right?
That's force. You can think of it as a push or a pull. It's the external thing needed to change how an object is moving to accelerate it. And force, just like velocity and acceleration, is also a vector, has magnitude and direction.
Right. And often when we start analyzing these things, we simplify a bit, treat objects as point masses.
We often do, yes. It just means we ignore the object's size, shape, any spinning initially anyway. We just focus on its overall motion from one place to another. It keeps the math simpler while we get the main idea.
Makes sense. So with that groundwork laid, let's jump into Newton's first law, the inertia one.
Right, this sets the scene. The first law states, an object stays at rest, or keeps moving uniformly in a straight line, unless some net external force makes it change.
So the way I think about it is objects kind of resist changing what they're doing. If it's stopped, it wants to stay stopped. If it's moving, it wants to keep going just like that.
That's the core idea of inertia, yeah? It's a property linked to mass. And that phrase, uniform motion in a straight line, is vital. It means constant speed and constant direction. So if anything changes speed or direction, the first law tells you there must be a net force at play.
Like a satellite orbiting Earth.
Exactly. It's not flying off in a straight line because gravity is constantly pulling it, changing its direction. That's the force.
And the law hints at something deeper too, doesn't it? This idea of inertial reference frames.
Oh, absolutely. It implies there's no single right place to be considered at rest.
Yeah.
If you're on a smoothly moving train, constant speed, straight track, you feel at rest relative to the train, right? Someone outside sees you moving.
Yeah.
But physics works the same for both of you. There's no experiment you can do inside the train without looking out to prove you're really moving or really still in some absolute cosmic sense. It's all relative to who's observing as long as they aren't accelerating.
That's quite a thought. Okay, so first law, need a force to change motion. Second law tells us how that change happens.
Precisely. Newton originally put it in terms of momentum. Momentum is just mass times velocity.
Yeah.
He said the change in motion, the change in momentum, is proportional to the net force applied, and it happens in the direction of that force.
Which we usually see as the famous EFMA equation.
Yes, for cases where the mass stays constant, that's what it simplifies to. Net force equals mass times acceleration. And it's so powerful because it quantifies it. Put a bigger net force on something, you get more acceleration. Put the same net force on something with more mass, you get link acceleration. Mass resists that change.
And you keep saying net force. That's important.
Crucial. Forces add up like arrows, like vectors. If you have forces pushing in different directions, you have to find the overall combined effect, the net force. That's what determines the acceleration in EFMA.
So if all the forces balance out perfectly, vector sum is zero.
Then EFTA tells you the acceleration is zero. That's mechanical equilibrium. The object's velocity isn't changing. It's either staying still or it's moving at a constant speed in a straight line, just like the first law described.
It's interesting. The source material points out that ESMA isn't just defining force. It's a real physical statement.
That's a subtle but really important point. We can often measure force independently. Think of stretching a spring scale. And we can measure acceleration independently. EFMA connects those two measurable things. It's the statement about how the universe works, not just how we name things.
Right.
And while EFMA is super common, The momentum version, FDPDT force, is the rate of change in momentum is actually more fundamental, especially when mass changes, like with a rocket.
Ah, okay. Which kind of leads us nicely to the third law, the action-reaction one, which, let's be honest, gets misunderstood a lot.
It really does.
Yeah.
Newton's third law. To every action, there is always opposed an equal reaction. Or, as he also put it, the mutual actions of two bodies upon each other are always equal and directed to contrary parts.
And the absolute key thing here, the thing everyone should remember, is these forces act on different objects.
Yes. That's the number one source of confusion. Let's use the classic book on a table example. Okay, Earth pulls the book down. That's gravity. That's the action. The reaction to that specific force is the book pulling the Earth up with an equal gravitational force.
Wow, okay. So the Earth is being pulled up by the book, even if it's tiny.
Infinitesimally, yes.
Oh.
Now the table pushes the book up, stopping it falling. That upward push from the table is not the reaction to Earth's gravity on the book. It's a separate interaction. The table pushes up on the book. That's part of a different action-reaction pair. The other part of that pair is the book pushing down on the table.
Got it. So two pairs. Earth pulls book, book pulls Earth, and book pushes table, table pushes book. Each pair equal and opposite, acting on the two interacting things.
Exactly. Think about walking. You push backward on the ground with your foot. That's the action. The reaction is the ground pushing forward on your foot. That's what makes you move forward.
Or a rocket.
Yep. Rocket pushes hot gas backward. Action. The gas pushes the rocket forward. Reaction.
And there's a deeper connection here, too, isn't there, to conservation of momentum.
Absolutely. If you look at just the two objects interacting, say the rocket and its expelled gas as a closed system, their equal and opposite forces on each other mean that the total momentum of that combined system doesn't change. Any momentum the rocket gains forward is matched by the momentum the gas gains backward. It's fundamental to how momentum is conserved within interactions.
Okay, let's put these laws to work. How do they explain something like free fall?
Free fall is a great example. Mainly second law plus gravity. The force of gravity pulling down is F is mg. M is mass, g is acceleration due to gravity. The second law says net force is F equals ma. So if gravity is the only force, mg equals ma.
And the m, the mass, is on both sides, so it cancels.
It cancels out, which is why, ignoring air resistance, a heavy object and a light object fall at the same rate. Gravity pulls harder on the heavy one, sure, but it also has more inertia, more resistance to accelerating. The effects balance, giving the same acceleration, g.
Amazing. And projectile motion, like throwing a ball.
That's just free fall. But with an initial sideways push, gravity only pulls down. So assuming no air drag, the horizontal motion just continues at a constant speed. That's the first law. But the vertical motion accelerates downwards due to gravity. That's the second law. Combine constant horizontal speed with downward acceleration. Get that familiar curved parabolic path.
Right. It's why if you fire a bullet perfectly horizontally and drop another one at the exact same moment, they hit the ground simultaneously, assuming flat ground, no air.
Precisely. The horizontal motion doesn't affect the time it takes to fall vertically.
And Newton had that amazing thought experiment, didn't he? The cannonball from a mountaintop.
Ah, yes. Brilliant visualization. Fire a cannonball horizontally. The faster you fire it, the further it goes before gravity pulls it down to the curved Earth. Fire it fast enough, and as it falls, the Earth curves away underneath it at the same rate. It keeps falling, but never gets closer to the ground. It's in orbit.
Which is a perfect lead-in to uniform circular motion, like planets orbiting.
Yeah.
Even if the speed is constant, the direction is always changing.
Which means there is acceleration. The velocity vector keeps turning. For uniform circular motion, that acceleration is always pointing towards the center of the circle. Its size is v squared over phi, beer. And the second law says this acceleration needs a net force towards the center. We call that the centripetal force.
For planets, it's gravity. For a car turning, it's friction between the tires and the road.
Exactly. Whatever provides that inward pull.
Okay, what about things that wiggle back and forth, like springs or pendulums, harmonic motion?
Right. Those systems usually have what we call a restoring force, a force that always tries to pull the object back to some stable middle point, its equilibrium position. For a simple spring, that force is often proportional to how far you stretch or compress it, Hooke's law, F equals kx.
Okay.
If you plug that force into FMA, you get a particular type of equation, a differential equation. The solutions to that equation naturally describe oscillations, that back and forth motion. The mass's inertia makes it overshoot the middle, the restoring force pulls it back, and it repeats.
The sources also mention slightly trickier cases, like rockets losing mass.
Yes, and that really shows why FTPTT, the momentum form, is the more general version of the second law. A rocket's mass is decreasing as it burns fuel. The force isn't just accelerating the rocket's current mass. It's related to the rate at which momentum is being carried away by the exhaust gas. The force pushing the rocket forward is the reaction, third law, to pushing that mass backward. It's about the change in the whole system's momentum.
And that old fan on a sailboat puzzle.
The classic brain teaser. If you mount a fan on a boat blowing onto its own sail, does it move? It forces you to think carefully about the third law and system boundaries. The fan pushes air forward onto the sail. Okay, that's a forward force on the sail, but the fan also pushes air backward initially. By the third law, the air pushes back on the fan and thus the boat system.
Oh, right.
If the air just hits the sail and stops or disperses sideways, those forces might cancel out, or you might even get a slight backward push overall. To get definite forward motion, the system, boat plus fan plus sail, needs to push something external backward. Like if the sail efficiently redirects the air behind the boat, it really highlights needing to define your system and track all the interactions, especially with the outside world, like the surrounding air or water.
That example really pulls the laws together. Now, Newton didn't just conjure these laws out of thin air, did he? What was the thinking before him?
No, definitely not. Ideas about motion evolved over centuries. For a long time, Aristotle's views were dominant. He thought things had a natural place and basically wanted to be at rest. Motion, especially violent motion like throwing something, needed a continuous push.
Which sort of feels right, but doesn't explain why a thrown spear keeps going after it leaves your hand.
Exactly. That led to ideas like impetus in the Middle Ages, from thinkers like Philoponus and Burdon. The idea was that throwing something imparted this internal impetus quality that kept it moving for a while before fading. It was a step towards inertia.
And then came Galileo. He seems key for the first law.
Galileo was crucial. His experiments, real and imagined, like balls rolling down ramps, led him to conclude that an object moving on a perfectly smooth, flat surface would just keep going forever.
Yeah.
He grasped that core idea. Steady motion doesn't need a cause. Only changes in motion need a cause, force. And René Descartes helped clarify that this natural, unforced motion would be in a straight line.
So Newton's genius was pulling all these threads together.
Absolutely. Yeah. He took these developing ideas about inertia, Galileo's work, Kepler's laws describing how planets moved, his own invention of calculus, and his theory of universal gravity, and synthesized them into this single, powerful, mathematical framework, the three laws. He showed the same rules governed apples falling and planets orbiting. It was revolutionary.
And honestly, for most things we deal with day to day, these laws work incredibly well.
Oh, completely. Designing bridges, cars, predicting trajectories, even sending probes around the solar system mostly relies on Newtonian mechanics. On the human scale, they're fantastic.
But physics didn't just stop there, right? Where do Newton's laws start to, well, break down or need refinement?
They're approximations, extremely good ones in many cases, but not the final word. At very, very high speeds, close to the speed of light, weird things happen to time, space, and mass. That's the realm of Einstein's special relativity. DEMA doesn't quite cut it anymore.
And for really strong gravity, like near black holes.
Then you eat Einstein's general relativity. Gravity isn't really seen as a Newtonian force, but as a curvature of space-time itself. Objects follow these curves.
And what about the super tiny world? Atoms, electrons?
That's quantum mechanics. Things get probabilistic. You can't know position and momentum perfectly at the same time. The whole deterministic clockwork picture of Newton's laws gives way to something fundamentally different.
So Newton provided this amazing foundation for the classical world, which then turned out to be a sort of special case within these broader theories.
That's a great way to put it. And even within classical mechanics itself, physicists developed other ways to describe the same physics, things like Lagrangian or Hamiltonian mechanics. They use different mathematical setups, often based on energy, but they predict the same outcomes as Newton's laws for classical systems. Sometimes they're just more convenient for complex problems.
Thinking back to that third law, again, action and reaction on different bodies, it really forces a shift in perspective, doesn't it? Away from just one object.
It absolutely does. You have to consider the interaction, the pair of objects, the system. You can't fully understand why one object moves without considering what it's pushing against and what's pushing back on it. It emphasizes that motion arises from mutual interactions.
Which brings us quite neatly to our final provocative thought for you, the listener. Given that action and reaction forces always act on different objects, what does this fundamental principle of interaction imply about how we must consider entire systems rather than just isolated objects when analyzing motion?
It's a shift from focusing just on what happens to this thing to what's the exchange happening between these things. Really changes the analysis.
Thanks for listening. Write us your opinion in the comments on what does this fundamental principle of interaction imply about how we must consider entire systems rather than just isolated objects when analyzing motion. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.